So in session 8 we talked about what we meant by first order optics, which was a region where we were going to assume that we could represent the sine of theta by simply using the linear term of the Taylor expansion theta. But what do we use first order optics for? Well, in reality we use first order, or also called paraxial optics, to define a lot of the properties of our optical system. Things that would be difficult to define in more completely, simply because once we introduce aberrations, defining the properties of a system get a little bit more complicated. So in this ideal region where we don't really worry about aberrations is how we define things like the effective focal length, the entrance pupil size and the location of the entrance pupil, the exit pupil size and its location, the F number, often abbreviated with the F slash and then the hashtag here. So in the future, if you see this, that's simply meaning F number, but also image location, image size, also a lot of special locations in the optical system that we refer to as cardinal points or planes. These are the principal points, principal planes, nodal points, nodal planes, and focal points, focal planes. I'll talk more about the points. The planes are obviously simply perpendicular to the optical axis going through the specified point. We're going to spend some time talking about the cardinal points, so if you're not familiar with those concepts, don't worry. And then two very special rays that we use to define our system, referred to as the marginal ray and the chief ray. Okay. So now, of course, we're saying that the sine of theta is approximately equal to theta in this paraxial regime. So we're representing the sine of theta with simply a linear term. But trigonometric functions in general are not linear. But at relatively small angles, it's reasonable approximation for some situations. So what we're saying is that in a small region around our axis, so where the ray angle relative to the normal is relatively small, we're going to say that we can approximate Snell's law as simply n1 theta 1 is equal to n2 theta 2. Now let's look at this for a couple of situations. Let's assume we have an index of about 1.5, which is pretty typical for glass materials, although there is a wide range of angles of indices of refraction. But let's assume that ray is incident at an angle of 5 degrees. If I use this first order calculation to determine theta 2, again my only unknown, I end up with theta 2 is 3.331 degrees. If we actually use Snell's law, we see that it's actually 3.333 degrees. So we're off by 0.02 of a degree. Probably not overly important for most of the work we're going to do. But if I use that same index of 1.5, again an air to glass interface, if I didn't mention that before, so n1 is equal to 1, and I have a 50 degree angle of incidence, if I use the linear approximation, I say that the refracted angle is about 30.7 degrees. But if I use Snell's law, I get 33.33 degrees, and actually I think I have those reversed. The first order approximation should be this because it should scale with that. So here is where the error is. But what this is telling us is that this 3 degree error in the angle of incidence is unacceptable. So as the angle of incidence gets larger, the error becomes unacceptable. But as long as we stay within this paraxial region for our first order calculations, our answers are going to be sufficiently accurate. Another concept that we have to consider is what's called a critical angle. If we think about the term the sine of theta, whether it's theta 1, theta 2, the fact is the value of sine of theta can only range between -1 and +1. Okay? So if we think about our calculation of the angle at the index boundary being n1 over n2 sine theta 1 is equal to sine theta 2, if n1 over n2 is less than 1, What that tells us is any ray can exit because a valid calculation for theta 2 exists. But if n1 is greater than n2, so if you're going from a high index to a low index, if this value is greater than 1, then there is a limit on the values of the sine of theta 1 that allow you to calculate a valid value or angle for theta 2. Okay? So when we go from high index to low index, this limit is referred to as the critical angle. And in air, where the lower index is equal to 1, the critical angle is the inverse sine of 1 over the index of the material. So what this says is light incident on a glass to air interface beyond this critical angle will not be able to refract out into that air region, simply because it would create an invalid expression for theta. So what that means is the light gets reflected back in. It stays in the glass material. For an optic made of BK7 at about 550 nanometer wavelength, this TIR occurs at an angle of about 41.2 degrees. What this says is as light goes from the BK7 to air, as long as the angle at the interface is less than 41.2 degrees, the light will transmit out. Once it gets beyond that angle, no energy transmits. All of the energy gets reflected back inside the higher index material. So now let's talk a little bit about the cardinal points. Cardinal points are basically reference points for our lens or optical system. The cardinal points are located on the optical axis, and they are part of the definition of a rotationally symmetric optical system. We use these reference points to approximate the system performance and behavior, and we use them to define the behavior of these idealized paraxial rays as they propagate through each of these spaces in the optical system. And again, the cardinal points include the focal points or focal planes, principal points or planes, and nodal points and planes. So let's talk about the focal point. Okay? The definition of the focal point. A focal point is a point on the optical axis where light from an infinitely distant point source comes to focus. So in other words, if I have collimated light coming into my optical system, it will form an image at the focal point. Okay? If I have light that starts from the focal point, then it will exit the optical system traveling parallel to the optical axis. So in this case, I have collimated light coming in, converges to a point at the focus. Here I have a point source at the focus, and it diverges outward from that source location, and I have collimated light or parallel light in image space. We saw previously that if I have light coming in from any other point, for instance a near point in the system, then I will also form an image, but not at the focal point. Okay, so the focal point does not define necessarily where the image is formed. It only defines where the image is formed for light coming in parallel to the axis. Now the principal points. These are the intersections of rays. If we take the intersections of rays extending linearly from object space to image space and ignore the effects of refraction, we're going to define our principal points or principal planes. The important point, sort of a bad choice of words, the important concept behind the principal points or the principal planes is the principal planes define planes of unit magnification. So since they both define planes of unit magnification, the principal planes are actually conjugate to each other. When we talk about the effective focal length of an optical system, okay, we've talked about the focal point being where this collimated light reaches a focus, but the actual effective focal length, that number that we talk about to represent our optical system, is actually measured from the rear principal point to the focal point. It's not measured from the front of the optical system to the focal point. It's not measured from the back of the optical system, typically, to the focal point. It's measured from this rear or second principal point. Okay? If you have an object and an image, and they're not both in air, then there is a relationship between the object and image focal distances that is simply related to the indices in those two media. But if we're talking about a system in air, then the front focal length is going to be equal to the back focal length. And in this particular case, I have a system in air, and you can see that these two distances are indeed equal, certainly to any approximation that we can make by looking at it. Alright, so when we come back in the next episode, we're going to talk a little bit and look graphically at focal length and principal point locations. So thank you.